In day 1 of the notes, we're just going to follow the directions. It says, suppose a ball is thrown up in the air with an initial velocity of 50 meters per second, with time equaling 10 seconds. The ball accelerates uniformly at negative 10 meters per second. We're going to draw an acceleration versus time graph of this motion on the rightmost graph. So, if I put 10 down here, negative 10, negative 5, negative that's positive 5 then, and positive 10 meters per second squared, we know that across the 10 seconds that it will start and stay at negative 10 meters per second. And then it says draw an acceleration, draw a velocity versus time graph of this motion. So on the middle graph, we know that it starts at a speed of 50 meters per second. 50 meters per second. 1, 2, 3, 4, 5. Oops, 50 meters per second. 10, 30, 20, 40. And so we're going to start from 50. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And across, if I drop by 10 every single second, here's at 5, it crosses here. And it goes from corner to corner almost, down to negative 50. So we're going to label VO, VF, and when V equals 0, and we're going to find X by calculating the area underneath the curve. So if I'm finding X by calculating the area under the curve, it's that distance and that displacement. And it says, draw an X versus time graph of this motion. Label the highest part of the graph as the top. 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 11 of these. And 1, 2, 3, 4, 5, 6, 7. And this is up at 10. So if I go by 15s, every line is 15, I should be okay. Because I need to go up to this area, being 50 times 5 is 250, but it's cut in half because it's a triangle, so 125. So this is also negative 125. So on the first half, we'll get all the way up to 1, 2, 3, 4, 5, 125. A second before that, we're only 5 away, because that's this triangle right here. And then 15 away, because 15 away would be this triangle right here. You could measure it. You could say that it goes from 10 to 20, and so the average of that is 15. This one goes from 20 to 30, so the average of this is 25. And the average of this is 35, and then the last one is 45. So, we know that we start at 0, and the first one is 45, and we also know that the next one, we're going to add 35 to that, so that's 30, and a little more. And this one is 5, 15 away. So now we have our arc going up to the very top, and the same thing, let's see, 5, 15, 25, and there's a parabola. So now we have our X graph drawn. We're going to label the highest part as V top, even though that's a displacement. That's what they told us to name it. So what is the velocity at the top of the flight? So at the top of the flight, well, that's the top, is 5 seconds along, and so at t equals 5 seconds, we're at v equals 0. The velocity at the top of the flight is 0 meters per second. And the acceleration due to gravity at the top is still negative 10, because that's at 5 seconds, and so we have negative 10 meters per second squared. How is VI related to VF? If this is just speeds, they're equal, but they're also opposite in sign if we're talking about velocities. So, have the same magnitude, but if I asked you about velocity, that'd be represented with an arrow. But then these individual points could also be VO and VF, like they told us to label. And so I could say that they are opposite in direction. Where is the ball's speed at maximum? Well, that would be at the beginning and the end. So V0 and V final. How is the distance the ball travels up related to the distance the ball travels down? They're both 125. So the distance is equal. What about the time up related to the time down? It's 5 seconds up and 5 seconds down, so it's equal. What is the average velocity for the entire flight? For the entire flight, we have 50 and negative 50, so the average is actually 0. The average velocity for the flight up is 25, and down is negative 25 meters per second. And so you can see how those average out as well. The average of the averages. So, the acceleration due to gravity is a value of 9.81 meters per second squared, and for estimates we use 10. The acceleration due to gravity is a constant rate of acceleration. It is negative because of its direction, which makes sense because over here it says it always acts down or towards the center of the earth. And so if we want up to be positive, then down must be negative when we're talking about how things are displacing. The acceleration due to gravity is independent of mass. So 100 kilograms on Earth weighs 100 kilograms on the moon, except 100 kilograms on Earth has a mass of 100 kilograms on the moon. The weight of 100 kilograms is actually 980 newtons down. On the moon, it would be 165-ish newtons down. In a vacuum, there's no air resistance, so everything falls the same. A hammer and a feather would fall the same. The only thing that keeps a feather from falling just as fast is that it is got the ability to catch more air with its wispiness. But you've seen feathers, if they're attached to like arrows, they can fly through air. It's a matter of the way they're facing and how they catch the air. A ball thrown upwards. When a ball is thrown upwards, its velocity is positive, upwards, but its acceleration is downwards, negative. At the highest point, a ball thrown upwards has a velocity of 0. But its acceleration is due to gravity, right? So is still 9.8 in the negative direction, meters per second squared. or downward. You could say downward or negative, but not negative down. Use your kinematics equation to solve the problems. They're a case of uniform or constant acceleration. So if there was no acceleration, things would fall at speed is equal to distance over time. But because of the uniform acceleration, you need to know that Vf squared equals Vi squared plus 2ax. You need to know that Vf equals Vi plus at. You need to have memorized that we are talking about x equals Vit plus 1/2 aat squared. And the last one is like it. X equals Vit plus 1/2 Vf minus Vi times t. This, by chance, is the first graph. If you notice, it has a squared, and so that parabola that we drew has a negative acceleration downward, so that way it's curved and concave down. This would be our initial intercept, so it has an initial speed, its initial slope. This one is the speed as it relates to time, so this is the second graph. Okay. And then this one happens to be the area of this first graph. The area of the second graph, which happens to relate it back to the first graph. So, write down the three primary equations. When Vf is not in the problem, we have x equals Vit plus 1/2 aat squared. When x is not in the problem, we have Vf equals Vi plus at. When t is not in the problem, we have Vf squared equals Vi squared plus 2ax. And so when we do these problems, we have our givens, which looks like it's just 2 seconds, but don't forget, anything free falling, anything starting from rest free falling, is going to have a Vi equaling 0 meters per second. If it's at its highest point, Vi is 0 meters per second, and the acceleration is negative 9.8 meters per second squared. So we can have some hidden givens. We have our 3 givens. We have our unknown velocity final. So we can find Vf equals Vf equals Vi plus at. Vi is 0, and we're going to add to it negative 9.8 times time, 2 seconds. So I got negative 19.6 meters per second. They got negative 20 because they used 10. A lot of these act the same. We did number 3 in class, so try it. I'll show my work in a little bit, or you can pause the video now. We have a distance, or an x, equaling 30 meters. We have a Vi equaling 0 meters per second. We're looking for the time and the speed both, so I know my acceleration is the other given. That's negative 9.8 meters per second squared. And crazy enough, we know a couple of things. First off, we know that this displacement, the flower pot falls a distance of 30 meters. So its displacement is actually from top to bottom, negative 30. And then Vf equals a negative number, and t equals, we're looking for that, those two. So So if it asks us for the time first, we can say that we have x equals VIT plus 1/2 AT squared, because we have x, we have VI, we're looking for T, and we have A. This would normally be avoided if you're looking for T unless VI is 0. Because VI is 0, this whole term gets crossed out. Or what you could say is that you plugged in 0 times T. And so 0 times 3, 0 times 4, 0 times 5, doesn't matter what the time is. Our VI is still 0. So I have x negative 30 equaling 1/2 negative 9.8 times T squared. And that means we have negative 30 times 2 divided by 9.8. And we see why we have these two negatives, because for that to be equal to T squared, we need to take the square root of both sides. 60 divided by 9.8 is about 6, and so 2.5 seconds is probably close to the square root of 6. To find the speed without having done this and finding the time, it'd be VF squared equals VI squared plus 2AX. But now that we have the time, you could actually do VF equals VI plus AT. Let's go ahead and solve it this way. 0 plus 2 times negative 9.8 times negative 30. Again, two negative signs to cancel out. The velocity final is velocity final squared. So 2 times 30, 60, divided by times 9.8 now is about 600. And then we take the square root of both sides. And so when we take the square root of both sides, it's very important that we have these two negatives that cancel out. But of course, the source information is important for us. So even though we have 24 meters per second, or it's like 24.5 or something like that, even though this is our answer, it's technically Math World has plus or minus 24.5 meters per second. And I picked the negative because what direction is it going? Well, it's falling.